So we were talking about the distance between u and v. That's a u vector right there. And this one is a v vector right here, right? Let me make sure that. So u, v minus u is going to be this vector, which is heading towards v.
Okay.
And the distance between, the distance of v minus u is going to be the magnitude, right, of the v minus u. And we already know that. What does it mean when we do the subtraction? For example, a b vector. If they ask you what is a b, now this a point is a vector on the same time, right? If you join that line right here,
Okay.
yeah. So that's a vector, and that is also a vector. So somehow they're talking about right. So they're talking about the differences. It's the same thing. A b means you're going to make a vector that is going from b towards a, right? Sorry, from a towards b.
Okay.
A b vector is going. And let me make it a little bit bigger. So that we write it OB minus OA. It's the same thing. We are going towards B, like A, from A to B. Starting point is A and end point is B. So when you head towards B, and you can also call it B vector, that's the A vector. So AB vector is B minus A. So this idea is important. And the distance of AB is equals to B minus A. Subtract them and then find the length. Now, if the A point, they're going to give you both of them. If the A point is negative 4 and 1, and the B point is 2, 3, then AB is going to be B minus A. So how do we do? Subtract them. We do 2 minus 4, and then comma, then 3 minus 1. And it's going to look like them, like a vector form or a point form.
Okay.
It's the differences of x component and the differences of y component. So we got 6, and that's 2. Now the next thing is the magnitude. Can you find out the magnitude of AB? So that is that. And square root of 40 is, now you can break it down. Simplify that thing. 2 square root of 10 is the length of AB vector. So in order to find AB, we do OB minus OA, or simply this minus that, right? You're going towards B, so just remember that analogy. And I already explained to you why it should be right here, why the sum is in the middle, and this is there. So that's the old stuff. You can watch those videos or these slides, but that was important. So I review that thing. Now the next thing that we're gonna talk about today, let me check my book. Dot product and cross. Now product means multiplication of the vectors. As we can add them, subtract them, in the same manner there's a sense of multiplication of the vectors. and there are two kind of multiplications. One is a dot product, and then there's a cross product. So both of them have a multiplication sense, but this multiplication is not as usual multiplication of the numbers. For example, whenever there's a question like some number multiplied by 4. Now, the definition of this multiplication is you add 3 4 many times, right? That is the definition of usual multiplication. But this multiplication is an operation, we call it product, but it really doesn't mean that thing. It doesn't mean this usual multiplication. So we name it dot product and cross product. And now we'll talk about both of them. I'll explain to you what is the meaning of dot product and why it's different. Why do we have two cross product? I mean, why do we have two products in vectors? Now, let's assume we have two vectors, and they probably they are not an exact. They're like that, right? Like they're not starting from the same point. Well, we can always move them. You can draw up vector which is exactly like the other one, right? Like the distance and everything. So we can always replace them. So this vector and that, they are same. So you can move them anywhere. So it's up to you. I move them and now they're intersecting. Now it looks like they're interacting, right? It looks more beautiful. But it's all good if you draw them like that and then ask about adding them or subtracting or multiplication. So you can, for example, this one can be like if you move this one, doesn't look like parallel though, but you can move it and make some nice intersection. Now, the dot product is a scalar product. We call it a scalar product. That means when you multiply two vectors, let's say u and that is a v product. So u, v are vectors in R2 or R3. That means 2-dimension or 3-dimensional plane. And dot product for these two vectors can be defined as u dot by v equals to, now let me write u. U is going to look like something u1 v1, right? u1 or let me write u1 u2 and v is v1 v2 v1
Okay.
v2 looks good. And the dot product, most of the time for vectors they use these arrows, but your textbook doesn't use these arrows. That means you're distinct you're distinct making a distinction between a scalar and a vector quantity, right? So these are the scalar numbers and this is a vector which looks like that. I mean, it has a direction, and direction is originated from origin going towards the point where we have that. So the dot product is defined as multiplication of the corresponding coordinates. That means u1 multiplied by v1 and then plus sign between them, u2 multiplied by v2. So that is the definition of that in R2. And we can extend it in R3. We're going to multiply, for example, if you have R3 plane, we're going to have a third like u3 and v3, right? Then you times these guys as well and write them here. Got it?
Yeah.
Or you want me to explain it more? The third one? Like in 3D?
Maybe like an example, just so I
Yeah,
can see how you
sure.
do it with the question.
Yeah, that's the next step I'm going to do. I'm going to explain you through an example. Now, we assume that u is 1, 2, and v is that point, and that point is somehow representing the vector. Right, so the points that we have, 1, 2, let me zoom, that's 1. So 1, 2 is going to be somewhere there. And 3, -4, -4, somewhere there. And when you meet them with the origin, it's going to look like some vectors. And now these vectors, we have to do the dot product of them. So how do we do that? Now there's no visual representation of the dot product or scalar product. Now why we call it a scalar product? The dot product is also not known as scalar product. We call it a scalar product because your resultant or your product is going to be a number. For example, dot of u and v is equals to 1 times by 3. 1 times 3 is 3, plus sign 4 times by negative 8, 4. 2 times by -4 is -8. Now we got a number. -5 is a dot product of u and v. And that's your u, this is your v. So you can write here u vector and that's the v vector. So the product of them is just a number, and the number we also call them scalars because there's only scale. We don't know where this number goes, in which direction that number goes. Number doesn't have a direction, so that's why we call it scalar quantity. These guys have a direction. Now we know that u is starting from 0, 0, goes towards 1, 2 point, and hence that is a vector, right? Whenever you look at a point from the origin, right, we get a direction. Then there's a direction when you think from the origin.
Okay.
So every point is related to the origin because its existence exists due to the center of the reference plane. So every point is a vector in a reference plane. So those are the vector quantities, but a number itself is not a vector. I mean, you're not, you can say that this is 0, 0 and that's -5, but still until you state it, it's not a, and whenever we talk about a vector, it's going to be 2D or 3D. Because in 1D, there's only one direction. In one dimension, we call it our real line. There's only one direction. You go in this direction, or negative of that is going to be that, right? So there's no other direction. So the vectors are going to be in the same line. So there's the same direction. So there's no other direction. So there's no meaning of direction. But there we have the numbers, same directions, right? I mean, different directions. For example, in a real line, in R1, 0, that's 1, and that's 2. Now, these guys, if you make a vector, still they have the same direction. So they are not they are not distinguished by the direction. They have the same direction. So there's no meaning of discussing the direction in R1. But that's the deeper concept. So all you have to remember how to multiply them, and the scalar quantity, we call it scalar product. So the resultant is a scalar number of the dot product. So now we have two kind of multiplications, dot and cross. As we know that dot product is going to give you a scalar number, but the cross product is going to give you a vector quantity. Let's talk about cross product, or we also call it vector product. Why do we call it vector product? Because your outcome is going to be, your resultant is going to be a vector quantity. Now, we can talk about this thing probably in the next chapter, but I'll show you what it's gonna look like, because the theorem number 1, theorem number 2, and the rest of the theorems on page 15, 16, 17 are related to the dot product, but I'll give you a glimpse of the cross product. So in cross product, for example, this vector, when you cross it by that, the cross of these two in a plane, which is a 2D plane, is not gonna be in 2D. It's gonna be in 3D plane. So, rather, you understand what I'm saying? The cross product of them is gonna be perpendicular to both of them, so it can be better understand in the 3D plane.
How is it perpendicular to both of them if it's just like one?
What do you mean by one?
Like, isn't it just one like line?
Yeah, let me show you through that.
Okay.
Let's assume there is there's a vector. Let's say this point is representing that, and there, that's the y-axis, and we zoom, there's another vector right here. Now the cross of them is gonna be perpendicular to both of them, so cross of them is gonna be right here, the z coordinate. That's the x coordinate, this one is y, and this is the z coordinate. So we have a plane right here, and right, that's the 2D plane right there. I should draw. So anything in 2D, if you take cross product of any vector in 2D, it's gonna be in 3D. Like, for example, a corner of a room. Let me give you one example. All right. So let's assume that is a room, and one of, let me draw the whole thing, it's gonna be good. Those slides are not visible. You can visualize that box in 3D, right?
Yeah.
Now, in this case, if that is one of your vector, and there's another vector right there, the cross product of them is gonna be right here.
Okay.
Yeah. It's perpendicular to both of them, making 90 degrees angle with both of the vectors. So if that is u vector and this one is v vector, then this is gonna be u cross v. It goes perpendicular to both of them. So let me erase that part because we don't need it. Yeah, so the cross product, most of the time we're going to do these lines. There's a vector, there's another vector on a plane. They're on some common plane, u, we, and their cross product is right here. So cross product is making 90-degree angle with both of them, u cross v. Right? Like you put two pens on the table. This is a one pen. There's another pen, and then there's a pencil which is standing vertically. Wherever they meet, is standing up. So the direction, now it's important. If you do u with, now try to understand this thing. If you do u with v, then it's gonna go upwards. Let's bring it close to us. If you do u with v, then it's gonna go up. But if you do v with u, it's gonna go perpendicularly down. That means it's gonna be right here. So when you go v minus v cross u, its direction is gonna reverse. So again, when you go from, it's a thumb rule. If you do thumb rule like that, you're going from u towards v, it's going up, and when you do v cross u, it's going down. Does it make sense to you?
I think so.
Again, explain you via hand gesture, if that makes sense. For example, this is u and that's v. When you go u cross v, it's gonna go up. Right?
Okay.
Let me show you by two pens. There's that pen and there's the another one. Like
Okay.
that. When you do u cross by that, now you're going from this direction to that. Right? So by thumb rule, it's gonna go up perpendicular to that, from here to there. But when you go from this blue side to this pen, then I do this from blue to the white. It's gonna go perpendicular in that direction. So your hand gesture, you're starting from the white one, going towards that, right? Going towards the blue. So perpendicular, it's gonna go up like that.
Okay, makes sense.
Good. So let's back to yeah, so that was that. And now we'll do a couple questions related to the dot product, and later on I'm going to explain you the vector product or the cross product. So we call it cross product or vector product because your resultant is a vector. Your outcome of the cross product is another vector. That's why we call it vector product. But in scalar product, your outcome or your result is a number, a scalar quantity, like that. I hope that makes sense to you.
Yeah, I think so.
Now we do a couple theorems related to the cross dot product, and let me have a look at